So good afternoon, good morning, and good evening, and welcome to LINSTOR Days software-defined storage virtual event. In today's sessions, LIN-BIT and our great partner Western Digital will present common future project related to cloud gaming and the synergy between LINSTOR and WD OpenFlex. And I would like to introduce the presenters. So first, Mr. Berger, Manfred Berger, is a Senior Manager Business Development Platforms for Europe, Middle East, Africa, and India at Western Digital. Manfred started his career in the year 81 as a test engineer at the IBM Storage Systems Division. Through two consecutive acquisitions, the former IBM hard drive business unit eventually became part of Western Digital Corporation. During his 50-year career, Manfred has transitioned through various engineering and business management roles before he took responsibility for WD platform business in 2015. Phil Freisner is the CEO of LIN-BIT and one of the founders. He holds a Master of Science in Computer Science from the University of Technology in Vienna, Austria. While graduating, Phil initiated the DRBD open source project, which is one of the technologies commercialized by LIN-BIT. Additionally, he occasionally speaks at Linux and open source events and is an active contributor to the Linux kernel. We'd be happy to answer questions in the Zoom Q&A chat section. So any question you may have, please type it, write it down, and we will be happy to answer at the end of the session. Okay, let's start. So please, Manfred, please start the webinar and share the slides. Thanks a lot.
Thank you very much. So I hope you can see my screen already. I am sharing. So I'm going to talk about gaming in a disaggregated IT environment. If you're not familiar with disaggregation, I hope you'll understand at the end of my pitch. Before I go into details, I have to make a statement here, a disclaimer rather. We're a publicly listed company, so everything we say is true and represents the best effort. At the moment the presentation was created. Should you decide to invest in Western Digital and make money, we're happy for that. Should you lose money, we take no responsibility. And with that, let's continue. Thank you. This is the storage portfolio of the Western Digital Corporation. Just a second, someone is trying to call me. We basically make everything from embedded NAND chips for mobile phone to hybrid servers. The lower line, and now my focus is gone, thanks for calling. The lower line represents our enterprise product portfolio, or the data center portfolio in other words, and the three products on the bottom right are the platforms I'm in charge of, which can be direct attached storage, JBOD and JBOF, can be storage servers, HDD or SSD based, and the focus product of today is OpenFlex, which is actually network attached storage. E3000 is the OpenFlex chassis. It's a 3U unit taking up to 10 storage devices that are based on NVMe drives. Every device has its own 2 times 50 gigabit Ethernet links. So if you scale capacity, you're gaining bandwidth and have a stable mix across the growth path. Up to 10 devices can be hosted, which gives us a total capacity of 614 terabytes in a 3U form factor, which to my knowledge is the densest you can have today. Looking at it in more detail, on the left-hand side, you see the actual storage device. This can be an F3200 or F3100 for the time being. Both are running on Ethernet, utilizing the ROCE V1 or V2 protocol. All of them have dual QSFP28 connectors, which deploy 25 gigabit lanes. And with that, you also find the answer to the question, why is this not PCI Express based? It's purely since Ethernet is technologically advanced and gives you higher bit rates per lane. The device consumes about 140 watts each, comes with 2 endurance levels depending on your write workloads, and in a total of 6 capacities. And best of all, with a latency of less than 50 microseconds, which is actually faster than a local SAS drives. And this is measured on client level, so the number that really matters. On the right-hand side, you see the back of the E3000 chassis. You see the 10 pairs of QSFP28 connectors. And key to it all, you also see the BMC management port. That is the port through which all the devices are managed and monitored. and through which you would create storage space on the device for sharing with external clients. There's a couple of status LEDs. PSUs are dual redundant, as you would expect. And then there's 4 fans keeping the whole thing nice and cool. Key question, why ROCE? If you compare ROCE and TCP side by side, where ROCE, maybe I should explain, stands for Remote DMA over Converged Ethernet, and DMA in that stands for Direct Memory Access, which means the network attached storage appears like local storage, writing its data directly into the client's memory with no CPU workload. But again, comparing side by side, TCP and ROCE transport, they look very similar, but the key difference is here in the center, where the average latency or the contribution of the protocol on average is 14 microseconds for the ROCE protocol, more than twice that for the TCP, but even worse, the distribution or the quality of service sees a spread of 26 microseconds for ROCE, but about 10 times that for TCP. So for real-time or very demanding applications, ROCE should really be the platform or the protocol of choice. Looking at the API through which the box is controlled, you see that on the left, we display the system health for the individual devices, the system utilization, and also the performance for individual components inside the system, which is just a general view, which you can zoom into should you need more details. But more relevant for this presentation is the device management through this API, where you create and manage local volumes, or to be more precise, namespaces on the NVMe devices inside, where individual namespaces are identified by a 16-byte identifier, which should be plenty for years and petabytes to come. You also control the volume access, which can be universal. So if you're in a trusted environment, basically every server can access every namespace on the box, provided there's an Ethernet switch in between. Or it can be fixed path, which is when you want to reserve certain resources for specific servers, then you would identify the IP path through which you want to make certain resources available, and people on other paths or devices on other paths will not have access. The simplest deployment is what I'm showing here on the left. As I told previously, the devices have dedicated Ethernet links. Therefore, if you connect one server to one device, that server has full access to namespace on the device. Servers next to it can only speak to another device. Up to 10 servers can share the box this way. But that's actually not disaggregated storage. That's almost like a direct attached deployment. On the right-hand side, that's where it becomes disaggregated, because you have one box sharing resources with many clients out there. And when I say many, we can have up to 2,560 namespaces on a single box, which can be a huge money saver, because typically if you have local storage on a server, the money on the SSD is spent, whether it's utilized or not. But if you keep it on a centralized box, you can assign it on an as-needed basis, and it wouldn't be left with any stranded storage. However, this deployment is fairly simple. Nice is that it doesn't need a server, but you don't have many functions beyond read and write. And this is where LIN-BIT with the LINSTOR software comes into the game, because there you could actually have a whole bunch of E3000 storage devices sitting in a storage network, which has a couple of storage servers and a data management server or metadata management server. And then you have a second client-based network where you can have thousands, literally thousands of clients sharing the storage resources managed by LINSTOR. It is desirable to have a lossless network to do all that. It's not mandatory, but it should be, because we're talking real-time applications here. That's why the switches in use should support two key functions. One is the priority flow control function, and the other one is the explicit congestion notification function. Overall, what that leaves you is not just a fast device, but also a big device, because this literally can scale to multiple petabytes. In our actual testing with LINSTOR from the client perspective, we got to about 380 megabytes per second per terabyte of available space under LINSTOR, up to 140,000 IOPS per terabyte, again under LINSTOR. In terms of density, I already mentioned it, we get to 205 terabytes per 1U unit height, which is relevant when you're planning big data centers. Moving on, there's a number of use cases that you could, or that we in fact have deployed E3000 to. They all have in common one thing, which is low latency, high IOPS, and high bandwidth. You might have seen previous announcements with a medical institution in France that's actually leveraging the E3000, but today's focus is on online gaming, which, to no surprise, also lives from low latency, high IOPS, and high bandwidth. There are several perspectives you can take. Here's the client view. Should you be a person that wants to get into gaming on day one, you would have to spend a good 4-digit number in terms of dollars to buy a powerful system with, let's say, 256 gigabyte SSD and so on. And on day one, all the money will be spent. After installation of the software, your storage will be utilized to about 10% for the operating system and maybe 1 or 2 initial games. You'll have had no fun yet with the box, and your hardware is utilized at about 3 hours a day, or in other words, 12.5%. There's another way for clients to engage in gaming. This is online gaming, which you can basically engage in with every smart device, be it a phone, a notebook PC, a desktop, or even a smart TV. You'll have spent no money on day one because it's a pay-as-you-go model where you pay the bill at the end of the month, and it's a double-digit dollar number. Switching views, if you are an online gaming provider, this is what you're in charge of. You would need a data center, good bandwidth to the outside, but focusing on the client once again. You would have to provide about the same 256 gigabytes of SSD storage spaces, but since I showed on day one, actually only 10% are utilized. This can be thin provisioned, which is a true money saver, and that's a function supported by LINSTOR. Everything else would be on demand. However, the SSD cannot be on demand because it will contain client data and therefore has to be reserved. But key, as I said, it can be thin provisioned. The typical I/O requirement, and I speak from real experience here, we do have gaming customers that base their business on previous products. This is the first time I'm actually speaking about OpenFlex in a connection with online gaming. But the typical performance requirements is 30 read-write IOPS of an average size of 64 kilobytes, or in other words, up to 2 megabytes per second. Looking at what we can actually do with the devices I'm showing in the rack, what's depicted here gives us 1.8 petabytes of net client SSD storage, or in other words, roughly enough to satisfy 20,000 clients at an assumed 33% utilization of the actual SSD storage space. And the good news, this is actually bidirectionally mirrored storage, so it is high availability storage as well. The 6 units I'm showing here can produce about 50 million combined net read IOPS at 4 kilobytes. And if you construct the combined throughput from those in terms of bigger blocks, this will be plenty to satisfy 50,000 clients at the before mentioned 30 read-write IOPS at 64 kilobytes. Having this extra headroom is a nice thing because you don't want to be running at the box's limit all the time, because games run in bursts, and if too many clients have new games loaded at the same time, you might actually need more than the average throughput. So it's absolutely a nice thing to have this extra headroom. The other function to point out is the 4 JBODs I'm showing here. They can give you a combined net 3.6 petabytes of RAID 6 protected backup storage. Where that comes in as a money saver is if a certain client is not active for whatever the time is, let's pick a month, then you could write the client's SSD image onto a JBOD and free that space for other users that have ongoing demand. And swapping that one back, should the client come back and log on again, will take less than 2 minutes based on the bandwidth and the combined performance of the drives in the JBOD. Moving on, I was talking about E3000 so far, which is the model we're presently shipping. We have already announced the Data 24, which is what I'm switching here to now. The big difference between the two, E3000 is based on devices containing multiple NVMe's. The Data 24 is a 2U box of slightly lesser density, because here we're talking individually exchangeable NVMe's. And in that case, the box is based on our latest model, the SN840. The other news with that box is, for the first time, we're leveraging our own network adapters. So every box comes with 6 RapidFlex network adapters, which are target NICs. So you couldn't use them as an initiator in a server. They're purely target, which is the function that's needed for the Data 24. In terms of API, we're leveraging the same functions that I showed on the E3000, so the two are actually exchangeable. Comparing them side by side, I will highlight 2 key differences, which may help you decide which ones you want. On the left-hand side, the focus is on density, but it leaves you with a chance to only change in 1/10 increments. You can only ever change a full device with all its NVMe's on the inside. And the links are specific to the drives. So whenever you add a drive, you add bandwidth. On the other side, the Data 24 with the discrete NVMe's, you can change capacity in 1/24 increments, which may be necessary for some applications. And it comes with more namespaces. So it's more suitable for clients that have a reduced need in terms of absolute storage, or where you want smaller increments. And also in the case of Data 24, the links are actually shared across drives by an internal switch, which also may have some implications on how you use the box and how performance scales over time. And with that, I'm done with my part. I'm now handing over to Philip. Just a second.
Yeah, thanks a lot, Manfred. Thank you for this overview of the OpenFlex hardware, E3000 and the Open Data 24, right?
Yep.
When we're going into this, I thought, well, shared storage, enterprise shared storage, this is where we are coming from, and it had some disadvantages. And my view of enterprise shared storage is it comes with the requirement for an additional network, usually the fiber channel network. It got redundancy in the box. You got very strong vendor lock-in from the individual drives. And that's not the case with these new Western Digital products. And rich feature set in the appliance. And this was not super nice. So where we are coming from with DBD and LINSTOR is a world of internal direct attached drives. So that imposes no real requirement on the network. Well, it should have enough bandwidth, but you can definitely go into a world of where you converge your networks. You might do software RAID within your machines. You definitely have no vendor lock-in. You are leveraging on the Linux stack for your storage features. But on the downside, when you have all those storage devices in your compute nodes, there might be, some stranded storage, which you are not actively using. And yeah, replication with DVD. And now let's look at these new, I came up with the term lightweight, but it's not an industry term, of course. This new type of shared storage. So it brings back the features of shared storage. So we have the perfect utilization. We're using NVMe over fabrics as an access protocol. So we can go with a converged network. We don't need all the extra gear to run a second network in the data center. It comes with not that many features, so it just gives us storage volumes, but that's perfect for our world because we want to add the features on the operating system level with leveraging on the Linux kernel. So I called it a reasonable vendor lock-in. And yeah, let's go into the details of the software stack. So I start here with giving you an overview of the architecture. So we have two main components when we look at the LINSTOR system. And one is the LINSTOR satellite. And the satellite it's a node agent. So there is no configuration at the satellite. There is no state at the satellite. It's just a process running somewhere. So in a regular system, you would install your RPM and use system cuttle to start it. That's it. In a Kubernetes environment, you would just roll out your stateless container. It runs on each of those nodes and you're done. And then there is the other part. That's the LINSTOR controller. In a conventional Linux setup, this would be a process that has an embedded SQL database. So it has a little amount of configuration, but it has definitely state. There will be standby controllers, so we can switch over to them. And the controller has the whole configuration of the cluster. So it knows where the satellites are running. It knows the IP addresses of the satellites. So the controller is the component that it establishes the TCP connections to all the satellites. A satellite can also be co-located on the same physical machine as the controller. And will use the satellites to, orchestrate all these storage volumes and storage devices and make volumes available. And what I should mention at this point here is that this control structure, so the LINSTOR controller and the LINSTOR satellites, they're only necessary for the control operations. So that means creating volumes, resizing them, taking snapshots, and deleting volumes and snapshots. The LINSTOR controller and satellite, this control structure is not involved in the data path. So that means, on the other hand, for all the established volumes, they continue to do I/O if we need to change something here, if we need to upgrade the LINSTOR controller, for example. And then what other components are there? The controller exposes a REST API. And on top of the REST API, you would usually use the CLI, but there are also the connectors using the REST API to interact with the LINSTOR system. Now, let's look at all this with an example. And I'm starting with the non-disaggregated architecture. So I'm starting with 6 nodes that have enough CPU and memory to run our workload. but also have built-in storage devices. And here on the slide, it's labeled with VM, but it could also be a container. So the same slide is also valid for a Kubernetes cluster. But it's also valid for an OpenStack cluster or OpenNebula cluster or an Apache CloudStack cluster. From us as providing the storage software, there's not a big difference between those. Okay, so we get in a request for a new volume, and let's assume for now that our policy in this storage pool is that we want to have two-way replicated volumes. Two-way replicated in order to be resilient against node failures, right? And so LINSTOR would try to place one replica on the node where the workload will run, and a second replica somewhere else. And the same is also true for the black VM. And that is a nice layout because all the reads can be carried out locally, not creating any load on the network, only the writes go through the network. But then, some live migration happens or a container gets redeployed somewhere else, right? Then the migrated workload, VM or container, is still able to do I/O, but now the reads go through the network. They might be read balanced, but they go through the network. And it takes either a time-triggered policy or a single LINSTOR command, and LINSTOR can actually migrate the storage to where the workload is. So if available in this volume group, it will create a new logic volume big enough to hold exactly this data. Then on the data plane side, DBD will copy all the blocks over while the application continues to run. And when that copy operation is finished, it removes the third replica, since in this policy, it only wants to have 2 replicas for each volume. Now, let's move on to the disaggregated world. And remember, disaggregation has the advantage that we reduce the amount of stranded storage. So that means we have the hypervisor that has enough CPU and memory to run the VMs and or the containers, but we have dedicated storage nodes. And the E3000 is a perfect example of that. But there would be a slight difference, and please excuse me that there are no tailor-made slides for that. In the case of the E3000, we access the storage target with the NVMe-of fabrics protocol, and then either have the DBD between 2 of the worker machines and then go from there with NVMe-of fabrics to the other storage node. Or we utilize the software RAID 1 of the Linux kernel here and have the 2 NVMe-of fabrics paths down to the storage nodes. And then here in the slide deck, I go through the example of that one of our hypervisor fails. Well, that's trivial. These virtual volumes are easily movable. So it moves to some other hypervisor, and here it runs with its VM or its container. And also if one of our storage nodes goes down, since we have 2 replicas, it's still up and running. And what looks pretty simple on these slides here, you need to picture that we might have thousands of volumes, and they are laid out, scattered across all the storage targets. And so on the slide, we only have one of those volumes, because putting 1,000 volumes on this slide, you will not figure out anything, right? So that was the principle by example. Now, when coming to this great E3000 shelves we have now from Western Digital, so LINSTOR supports the OpenFlex API. So that means that all these storage management requests coming down the stack through the workload orchestrator to LINSTOR can, schedule them, allocate them to the available target nodes, and it uses the OpenFlex API to actually create their NVMe-of fabrics namespace, or resize it, or delete it. What it doesn't outsource to the box is taking snapshots and thin provisioning. That part of the stack, that happens on the Linux machine. So on the machine where your workload is running. Then we found out that for Kubernetes, for example, in Kubernetes expects that the volume names used by Kubernetes are like 40 characters long. So we had to do here some remapping, I call it name extensions, for the OpenFlex world. And when you remember the architecture diagram from a few slides before, we have a satellite for each storage device. And here our satellite processes are not running on the enclosures itself, but a satellite is implicitly started on the controller node and it runs there. And I have here an example of a command when you manage a LINSTOR system. So adding a E3000 shelf to a LINSTOR cluster is as easy as running this command. So it's just a node create, OpenFlex target, the name, IP address, and I will set that this is some identifier for the hardware. Yeah, and what else is coming soon here in the area of shared storage and LINSTOR? So the developers are pretty far with support for LVM for shared storage and support for clustered LVM. So in context with the E3000, this gives us just even more flexibility how we could manage that. More flexibility. Okay, let's move on here. Now I'm switching gear to the upper layers of the stack, because it's nice that LINSTOR can manage the storage, can manage the hardware, but it should also, pass the storage to the upper layers, to the orchestrators. And what we currently have is Kubernetes, and there is the CSI driver most relevant, and also all the newer parts necessary in a Kubernetes environment. I will speak about that in a second. Docker Swarm was a topic, is no longer so hot anymore. OpenStack Cinder, of course. We have it in OpenStack upstream since April 2019, and this OpenStack release has the codename Stein. If you're in Stein or any newer OpenStack release, everything is fine. For all the OpenStack releases, you need to reach out to us. Then there is one driver for OpenNebula by LIN-BIT. There is even one driver maintained by the community, by Quaps. We will have on the LINSTOR phase tomorrow. There's a driver for Proxmox virtual environment. A driver for Xen server that is in late development stages. It already runs in the lab. It will be released very soon. And the work on a driver for Apache Cloud Stack that has just started. So I expect that to land before the end of the year. Now, since Kubernetes is such a big topic, let me quickly dive into that area of Kubernetes. So in Kubernetes, when you do software-defined storage for a Kubernetes cluster, these days it is expected that the software-defined storage software itself is managed through Kubernetes. And so this installation of the software is done by a component called a Kubernetes operator, or so-called YAML files. Then the Helm charts are connected to the YAML files. If I remember correctly, the actual driver is called the CSI driver. And the components are, of course, the LINSTOR controller that is packaged as a container, the LINSTOR satellite packaged as a container, and the so-called DBD module injector. And it can also inject other drivers necessary. So it can also inject the NVMe-of fabrics initiator and those parts. And last but not least, there is a component called Stork driver. And Stork is a scheduler extension for Kubernetes. So very high level description would be, it is a way we can influence the Kubernetes workload scheduler to take into account specific properties of our storage landscape. So it connects LINSTOR and Kubernetes in a more close way. And all that comes in two flavors for consumption. One is the pure open source. So pure. It's called Piraeus Datastore. So here all the containers are based on Debian. It's maintained by LIN-BIT, and we publish all that on Docker Hub or Quay.io for everyone. And it would do the module injection by recompiling from source on the box itself. All nicely automated, but you need to understand this is the open source lane. And then the, let's say, enterprise lane is here. So here all the containers are based on Red Hat UBI, Universal Base Image. So that enables us to get certified by Red Hat and for Red Hat OpenShift and Red Hat Core OS. And that comes with enterprise class support from LIN-BIT 24/7. And here, only available to the customers of LIN-BIT. Yeah, so in summary, LINSTOR covers you from, in some cases, discovering the hardware. In some cases, you need to tell it about the hardware. It uses LVM or CFS for basic management of the storage, for slicing it up for consumption on the node level. Then it adds all the features like replication, like encryption at rest, various layers of caching. So either SSDs in front of rotating media or PMEM in front of NVMe drives. And finally, it takes care how the volume is attached to your actual workload, either through NVMe-of fabrics, the DoD protocol itself, or even iSCSI. Okay, and with that, all of you survived my slide deck. I thank Manfred for the first part of the presentation, and I'm handing over to Daniel in the hope that we get some questions.
Let's see. Okay. No, I don't see any open questions in the Q&A, but we are more than happy to answer any questions if you have any. So feel free. Okay, with no questions.
Apparently, we answered all the questions before they were asked.
Probably, right. Well, obviously, you're welcome to contact Western Digital, LIN-BIT, and we'll be happy to answer questions afterwards. Information is available, and I would like everybody to join this short webinar today. And thanks, Manfred. Thanks a lot for taking the time to present. Thanks, Phil.
My pleasure.
And yes, and have a great afternoon, great evening, great day, great morning. Talk to you soon, and take care and stay safe.
Thank you. Have a good day.
Thank you.
And we're having another
Bye-bye.
webinar coming in roughly 1 hour, 20 minutes. I hope to see you there as well.
Hey.
It's LINSTOR versus competitors, cloud native industry comparison. And so stay tuned for that as well. And of course, 2 webinars tomorrow. But you can see that on the schedule.
Bye-bye. Thanks.
Goodbye.